The Science Screen Report, developments in science, engineering, and medicine that help solve the problems of modern life. Sooner or later, we're going to run out of oil-based fuels. The search is already underway for synthetic fuels, energy-rich gases and liquids made from organic substances, biomass, such as plants, surface and underground coal, shale rock oil, and other materials. This is a report on progress towards tomorrow's synthetic fuels. Short-term energy problems and declining stocks of petroleum have led to efforts to develop synthetic fuels. One such energy source is gasahol, made from plant material. In commercial gasahol production, corn is the main raw material. In this facility, enzymes help speed conversion of cornstarch to a sugary mash, which, fermented by yeasts, yields an alcohol-rich fluid. Proteins, oils, and other byproducts are used as animal feed. The alcohol-rich fluid is processed in distillation towers, the lighter ethanol separated out. The ethanol, combined with gasoline in a 1:9 ratio, is gasahol, sold as super unleaded gasoline with ethanol. Another biomass fuel is ocean kelp, which can be processed into a form of natural gas. Here, an experimental marine fuel farm is harvested using a special clipper-equipped ship. The cutter, a meter below the waterline, collects the plant's surface canopy of leaves and flotation sacs, leaving the body of the plant in the sea. When the ship's hold is full, it delivers the kelp to dockside for processing into methane. This overseas production facility, the largest in the world, currently converts coal to a variety of synfuels. The coal, 40,000 tons a day, is converted to gas in advanced gasifiers, first developed in the 1930s. Coal particles, averaging 4 centimeters across, are fed into the top, steam and oxygen injected into the base. When they meet, particle combustion yields hot gases. As these rise through the coal bed, the steam reacts with the unburned coal's carbon and volatile matter, producing hydrogen, carbon monoxide, and other hydrocarbons. A hot gas emerges from the top, coal ash from the base. Nearby, all the chemical products are separated, leaving only hydrogen and carbon monoxide, the chemical building blocks of synthetic fuels. The purified mixture of gases is injected into a chemical reactor, which is joined by a catalyst. The resulting reactions yield gases, liquid hydrocarbons, and water-rich chemicals. The water-rich chemicals are processed into a range of alcohols and ketones, the raw materials for plastics, paints, solvents, and other chemicals. The hydrocarbons go to a refinery to be made into diesel oil, jet plane fuel, and high-octane gasoline. Coal ash waste is used for bricks and road paving. Effluent water is purified and kept in a closed-cycle system. At Hope Creek, Wyoming, coal deposits not suitable for mining are being converted into synfuels through underground coal gasification. The process starts with the drilling of boreholes to the bottom of coal seams. The coal at the bottom of one well, the injection well, is then ignited. Air or oxygen and steam is forced into the coal seam, and product gases are drawn out of the other well, the production well. To better link the wells, explosive fracturing is used. The fractures allow gases to flow and react more readily. The first Hope Creek test began with explosive fracturing, followed by construction of the gasification system. Another process tested was reverse combustion, setting fire to the coal at the bottom of one well, then injecting air into the other so the air can move through natural cracks to the burn zone, producing a high flow rate that supports combustion. Sensors placed in the boreholes transmitted data on ground motion, temperatures, pressures, and product gas-water content, all recorded by on-site computers. This program demonstrated that underground coal not suitable for mining can be converted to products that may be upgraded into substitute natural gas, methanol, or gasoline. Oil shales are a third type of synfuels. A finely textured sedimentary rock, they hold the organic solid called kerogen, a high molecular weight hydrocarbon. Heated to 900 degrees Fahrenheit, it decomposes to yield oil. This project in Colorado was designed as the first full-scale shale oil extraction plant. Shale mining is carried out by room and pillar techniques, creating huge man-made caves. 20-meter square pillars support the mine roof. 3 double retort structures are designed to process up to 11,000 tons of shale ore daily. The raw shale is first preheated. Then, in a retort, a huge rotating drum, it's mixed with ceramic spheres heated to 1,300 degrees Fahrenheit. The spheres are periodically separated out, heated again, and returned to the retort. After several cycles, enough heat is transferred to raise the shale's temperature to 900 degrees, so its kerogen vaporizes. The spent shale residue is removed, and shale vapors condensed and recovered as liquid and gaseous products at 90% efficiency. The resulting shale oil is comparable to the best natural crude petroleum. Subsequent on-site partial refining or upgrading improves the shale oil's quality. Upgraded, the shale oil can be pipelined to an existing oil refinery for final preparation. In the American Southwest, 700 meters below this installation, underground shale oil production is being carried out. The process is called partial in situ production, both mining and extracting the shale oil underground. Huge man-made rooms provide access to the rock. Then machines drill holes that are charged with explosives. An engineering rendering of the site shows the man-made caves, each the size of a 30-story building. These void chambers provide room for the heated fragments of shale to expand. Explosives emplaced, the void chambers are evacuated of all workers. A triple check ensures no one remains below. Blast timing and sequencing are critical. To promote uniform chemical conversion of kerogen to shale oil, debris must be of uniform size and uniformly distributed in the retort. This precisely planned disruption is the basis of the new technology. Next, inert gas heated to 1600 degrees is injected, warming the debris so the kerogen gives up its shale oil. As the hot gas fills the retort, the shale oil drains to the bottom and is collected. Research is also underway on a number of other synthetic fuels, including tar sands and heavy oil. Like all energy sources, synfuels have their special drawbacks: many resource inputs, environmental problems, and possible social consequences. However, studies have shown that these can be forestalled or overcome. Oil and gas are not renewable resources, and in time, supplies may run out. The development of synthetic fuels will extend our total non-renewable energy supplies, hopefully until science and engineering perfect tomorrow's renewable energy sources.